Well, we were talking about mixed strategies. So what we had was, we had a game. And well, we said that the agents might randomize on their strategies. So from this game, we moved into its mixed extension, where the set of players is the same, but the strategy sets of the players are now probability measures on their original strategy sets. And then we extended the preferences over profiles of mixed strategies in such a way that we assume that the preferences satisfies the von Neumann-Morgenstern axioms. Hence, preferences had a von Neumann-Morgenstern, or just shortly, von Neumann-Morgenstern expected utility representation, or just shortly, an expected utility representation. Okay? So we call strategies in this set pure strategies, strategies in this set mixed strategies. And in a obvious, trivial way, we can think of the strategy set in the original game as a subset. Again, I'm saying think about it that way. Mathematically, it's not a subset. They're totally different animals. These are probability measures. These are functions. These are just simple strategies. But we can think as if it's a subset of it. How? Take a strategy in the set SI. We can easily construct a mixed strategy, which actually has the same effect, which is, so select, let's call this mu SI of I. So take the mixed strategy, which assigns the probability 1 to the pure strategy SI, and 0 to every other strategy. Okay? So that's what I mean by we can think of the set of pure strategies as a subset of the set of mixed strategies. For every pure strategy, we can construct a mixed strategy which selects the pure strategy SI with probability 1, and every other, and hence every other strategy with probability 0. Okay? A few words about notation. So this is just a regular game. Everything we had done, everything we have constructed, every theorem, every statement that we have stated before for general games also works for these games. Okay? So when I talk about, the Nash solutions of this game. So I will usually use the frame Nash solutions of the mixed extension of gamma. Okay? And several books, rather than calling that the Nash solution of the mixed extension or the Nash equilibrium of the mixed extension, they call it a mixed strategy Nash equilibrium of the original game. That means the same thing. So if you're following a different book and you see the phrase, the mixed strategy Nash equilibrium of the game gamma, okay, it's not a different solution concept. It's the same solution concept. It's the same idea. The only thing is the strategy set is different. So whenever I say Nash solution, Nash equilibrium of the mixed extension game, different economists, different game theorists call that the same thing, the mixed strategy Nash solution of the game gamma. Okay? So a warning about terminology if you're following a different book. Okay? So because of this, you see, this is too much writing. So I will just sometimes say, take the mixed strategy SI and delta SI. Okay? So again, mathematically, this is not meaningful, but we're abusing the language. So whenever I say this, I'll most of the time say the pure strategy SI in delta SI. What I mean is the degenerate mixed strategy, the degenerate probability measure which selects SI with probability 1. Okay? So we'll use this simple notation rather than writing mu I super SI and so on. Okay? So far so good? Okay. So last lecture we found the Nash solutions of the mixed extension of the Battle of the Sexes game. Today we're going to repeat the same thing but use a different method. But before we use that different method, I'd like to make an observation. So take a mixed strategy profile. Okay. So we're using, we assume that preferences satisfy the von Neumann-Morgenstein axioms. So we have an expected utility representation. So the number assigned by that expected utility representation to mu was, as we stated before, mu. Well, let me write it the open way. Ui Si I in n times ui of s. Well, let me write the, okay, well, s as an element of, okay. So that was the expected utility representation. We can write this as oh, I'm sorry. Using I here is not a good idea because I've used I here. So sorry about that. Let me use J. That's I. That's fine. Okay. So mu I Si times the product of mu J Sj, where J is an n minus I times ui. Okay, so I just took out the ith term out of this. Actually, I can write the summation as summation over Si, summation over the strategy profiles, the pure strategy profiles of the other agents. Okay, so I can take this out of this summation. There's no Si here. So what we have here is summation Si. Oops. I'll write this shortly as J different than I. Sorry, I forgot the summation. Now, if I look at this, okay, so think about multiplying this with 1. Okay, so I can think of this as the expected utility of player I when he plays the strategy Si with probability 1, and when the opponents, the other players, plays their strategies according to the probability distribution mu J. Okay, or shortly, we can write this as, so let me write this a little bit more explicitly. So that's okay. So that's the expected utility of player I when he plays the pure strategy SI with probability 1, and the rest plays their mixed strategy in the profile mu minus I. Okay? A very simple observation. By the way, this is a probability measure, so they're all non-negative and they sum up to 1, which means that the expected utility of player I from the strategy profile mu is a convex combination of his expected utilities, okay, of the expected utilities that he gets when he plays the pure strategy SI, where SI runs over capital SI, and the other players play according to their mixed strategies in mu. Okay? Very simple observation, just simple arithmetic. Very simple observation, but it's a very useful observation, and we'll make use of that. Okay? So keep that in mind. Well, actually, let's just start using it. So I'll write the Battle of Sexes game again. So there was the choice between soccer and opera. Okay. So we already found, well, again, by the Nash existence theorem, we know that this game has a Nash equilibrium. And actually, last lecture, using the regular method, we did find the Nash solutions of this game. So today, we're going to use a different method to find the Nash solutions of this game, which will essentially be based on this statement. So last time, what we did was, if you remember, we had PS, okay? So we denoted the probability that player 1 plays S with PS, and hence the probability that he will go to opera with probability 1 minus PS. And then we used Q to denote the mixed strategy of player 2. So we used QS, the probability that player 2 will go to the soccer match, and 1 minus QS, the probability that player 2 will go to opera. So last lecture, what we did was draw this. Okay? Now we're going to change things a bit. Rather than putting PS here, we're going to put QS. Okay? And rather than putting, so that's capital U1, S1, okay? So actually what I'm going to do is I'm going to draw graphs of this function, okay? So I'll put S for SI, and then I'll put O for SI, and then calculate the expected. So what is U1 of S QS? That's 2 times QS plus 0 times 1 minus QS. What is U1 of OQS? Again, we're abusing language here. Normally, I should put a mixed strategy here. So this is actually like the mixed strategy where he plays S with probability 1. So what is that? That's 0 times QS plus 1 times 1 minus QS. So I'll plot these. So that's easy to do. That's just a line. So this is U1 of SQS. And then let's draw the other one. Again, that's a linear function, slope minus 1. So it starts with 1. It's not a very symmetric picture, but okay. So remember, this is 1. So this is U1 of BQS. Okay? So far, so good? So, of course, what I need is this animal. Okay? But what we know is this animal, is a convex combination of these animals. So if I take any actually, let's use a different color. Any PS, 1 minus PS, what will it be? So for this given QS, it's going to be a convex combination of these two numbers. For this strategy of player 2, it's going to be a convex combination of these two numbers. For this strategy of player, this mixed strategy of player 2, it's going to be a convex combination of these two numbers. And the weights will always be the same. Okay, it's going to be PS times this plus 1 minus PS times this. PS times this plus 1 minus PS times this. PS times this, 1 minus PS times this. So when you do that, actually what you will get is this. So what we know is, as PS changes from 1 to 0, U1 PS QS will change in this manner. Okay? A very simple observation. Okay? Okay? Because it's a convex combination, the expected utility cannot be bigger than the expected utility, the maximum expected utility that he gets under a pure strategy, and cannot be less than the expected utility that he gets under a pure strategy. Okay? So far, so good? Well, once we have this picture, before I go to the next step, let's calculate this point. What is that point? That's the point where 2 QS is equal to 1 minus QS, right? So that's equal to QS equals to 1 over 3, right? So just by looking at this picture, I can easily conclude that B1 of QS is equal to, well, if QS is less than 1 over 3, so if we're considering a strategy, a mixed strategy of player 2, which is less than 1 over 3, so as PS changes from 1 to 0, his expected utility takes values in this region. And what is the maximum expected utility that he gets? It's this one, which is what he gets when he plays B for sure. That is, he plays PS with probability 0. If QS is bigger than 1 over 3, and we're in this region, again, we observe the expected utility that he can get changes in this region. The maximum he can get is this, which is what he gets when he plays the strategy S with probability 1. That is, PS equals to 1. Okay. So if QS is equal to 1 over 3, then what we see is no matter which mixed strategy player 1 plays, his expected payoff is always the same. Which means that, anything is a best response. So PS can take any value from 0 to 1. Okay? So far, so good? Any questions? Any questions? That's it. So that's the same result that we found, but this time we took a different approach. Okay? Usually when we were working with, I'll call regular games, not mixed extensions, we would draw UI given S minus I against SI. This time we draw the payoff of player I as a function of the strategies, in this case mixed strategies, of the opponent. Okay? And this was useful in this case. It's not useful. It was not useful when we were talking about Cournot, when we were talking about Bertrand. It was useful because of this property. The expected utility that a player gets from any mixed strategy is a convex combination of his expected utility that he gets from playing pure strategies. Okay? So far, so good? So far, so good? Okay. So I will not do the rest. You can, do the same thing with player 2. So plot U2 S2 against PS for different pure strategies of, well, the picture will not look like that, for different pure strategies of player 2. And again, play the same game. You'll get since we already solved this game, I will not repeat it. You see the technique, okay? So far, so good? So far, so good? Of course, these pictures work when players have few strategies, okay? So for example, well, this will work, for example, if player 2 had only 2 strategies. It doesn't matter how many strategies player 1 has, right? Here, because what matters is on this axis, keep things simple, I need a single number, okay? If player 3 had 3 pure strategies, then I would have to draw a 3-dimensional picture, which would be hard to draw and hard to comprehend. But if player 2 has only 2 strategies, it doesn't matter how many strategies player 1 will have. I will just have more lines. All I will have to do is observe those lines. Okay? We'll do an example with more players too. Okay? So far, so good? So let's think more about this. A very, very simple statement, very intuitive, but very useful. This, together with the picture that we just draw, what kind of conjectures can we make? Actually, let me draw the picture again. So we had this. We have this. Okay. A bit of notation. We will use, you probably saw this notion in probability theory, support of a probability measure, right, denoted, we will denote Did you have a notation for the support of a probability measure when you took probability theory classes? Do you have a notation for that? Okay, well, since you don't have a fixed notation, I will use SUP, P, not a single P, so I'll use this part. Okay, I don't want to get it confused with the sup and inf of a function. So the support of a probability measure mu I is defined as the set of all strategies, pure strategies of player I, which are played with a positive probability. Okay? So we'll use that notation. Take a strategy mu I of player I, which is a best response to the strategy profile mu minus I of the other players. Okay? So we took some mixed strategy, but it's a best response, okay, of player I. What can you say about the support of mu I. I just happened to erase that formula, but let me write that again. So the expected utility of player I from the strategy profile mu is a convex combination of his expected utilities that he would get when he plays the pure strategy, when he plays a pure strategy and the opponent plays the mixed strategy profile mu minus I. So mu I is the best response of player I to mu minus I. What can you conclude about this? So take a strategy SI in the support. That is, it's played with a positive probability. What can you say about that? Again, so once this is the case, it means that he's maximizing his expected utility. Okay? But when you look at this formula, his expected utility is a convex combination of his expected utilities from his pure strategies. So his expected utility cannot be bigger than the maximum expected utility that he would get by playing a pure strategy. So this should be think, think, think. Let's look. Okay, take this mixed strategy of player 2. Okay. What is the best response here? So this was U1 of SQ2. That was U1 of BQ2. So his best response was to play B. So the only thing which is in the support of this mixed strategy is B, right? But then that trivially, so B is a best response, implies that B is a best response. So not a very interesting case, okay? Take this mixed strategy of the second player. What is the best response of player 1? Any mixed strategy. For example, playing S with probability 1/2, playing O with probability. Why did I write B here? That's an O, right? Did I make the same mistake before? That's opera, soccer. Okay, so go to a soccer match with probability 1/2, go to an opera with probability 1/2. So both S and O are in the support. Okay, so if he plays O, what is his expected utility? It's this. If he plays S, what is his expected utility? It's the same. Which means that O is also a best response. That is, 0, 1 is also a best response, and S is also a best response. 1, 0 is also a best response. Okay? So this would imply that this set is, come on, wake up. You can see from there, right? Again, the simple idea. Okay. The support, again, the expected utility from the mixed strategy mu I is a convex combination, so it cannot be bigger than the biggest of these numbers. Okay? So you always have UI, mu I, mu minus I less than or equal to UI, SI, S minus I for some SI, right? For some SI, which is played with probability, with a positive probability. Because if it's equal to 0, it will not show up in the summation. Okay? Okay? But then, we know that this is minus I, that's a prime, for any mu I prime, which means that if mu I is a best response, SI should also be a best response, as long as mu I SI is different than 0. Okay? If it's equal to 0, it will not show up in the summation, so I cannot write that. Okay? So that implies this. And actually, we have the other way around, too. If SI and SI prime are both best responses to mu minus I, then they would yield the same expected payoff. Then their convex combination would also yield the same expected payoff. But that would also mean that mu I, the probability measure, which puts positive weight on those two, only in this case, those two strategies, will be a best response. So that's an if and only if. Okay? Again, just from this simple, very, very simple observation. Okay? Any questions? Any questions? Yep. Support is, yes, so this is actually, again, we're abusing language here. So today's class has become very abusive, but we're abusing language here. So actually, this is, strictly speaking, a subset of SI. These are pure strategies. But we interpret pure strategies as a mixed strategy, which that pure strategy is played with probability 1. So again, here I'm kind of abusing language. From now on, I will just write this, but you should keep in mind that whenever I say a pure strategy is a best response of player I in the mixed extension game, what I actually mean is the mixed strategy which selects the strategy SI with probability 1 is a best response. Okay? So far, so good? Any questions? Okay. Now, this is also very useful for the following reason. Let me see, do I want to write that next? Let's take a Nash solution of a mixed extension game. Again, whenever I talk about mixed extension, the underlying game we assume is finite. Okay? So what is that equivalent to? Well, that is equivalent to saying for any I in N, mu I prime is a best response of player I to mu minus I star. Right? But from here, what do we have? For any I in N, okay, support of mu I star is a subset of bi mu minus I star. Okay? Well, again, in the mixed extension game, so maybe I should put an M here. These are mixed extension games. Okay? But I will not, we will again abuse notation. So whenever you see a mixed strategy here, you should think about the mixed extension game. Okay? So what does that mean? For any I in N. So anything which is in the support is a best response. So it means that for any SI in the support of mu I star, what we have is capital Ui Si mu minus I star greater or equal to capital Ui mu I mu minus I star. For what? Actually, let me write it like this. So we will have this capital Ui Si mu minus I star greater or equal to I capital Ui mu I mu minus I star. For which mu I? For any mu I in delta Si. Okay? So far, so good? Actually, let me write this part. So this is also equivalent to, for any I in N, for any mu I in delta Si, capital Ui mu I star mu minus I star greater or equal to capital Ui mu minus I star. Okay? So that's where we start with. That's where we ended with. Okay? So this is something simpler to check because you check over pure strategies here. Here you have a mixed strategy. Okay? So to check whether mu star is a Nash equilibrium or not, it just says check pure strategies against mixed strategies, which will again prove to be useful. Okay. So how will we use this? Let me erase this part now. How will we use this, or what we just had here, in finding Nash solutions? Again, this, or actually, let me write that here again once more. So, how does that turn out to be useful? Let's take a Nash solution of the mixed extension game. Okay. So if it assigns a positive probability to two strategies, so take two strategies, pure strategies, Si prime, which is in the support of mu star, mu I star. What should the relation between capital Ui Si mu minus I star and capital Ui Si prime mu minus I star be? What should the relation between these two be? They should be equal, as your friend said, right? Well, because they're both in the support, well, because this is a Nash equilibrium, it means that mu I star is the best response to mu minus I star. Because mu I star is the best response of player I to mu minus I star, the support of mu I star is a subset of Bi mu minus I star. Well, which means that if Si and Si prime are in the support of mu I star, they're both the best response. But if they're both the best response, they should give the maximum expected utility given that the opponents are playing mu minus I star. If they both give the maximum, they should be equal. Okay? And this is true for any Si prime in this set, and for any agent. Okay. So this holds. Now let's take a strategy Si, which is in the support of mu I star, and a strategy Si prime, which is not in the support. What should be the relation between these two numbers? It should be just greater, or does it have to be strict? Sorry? That might also be equal. I will not write the whole thing. Okay? That's number 2. So actually, if mu star is a Nash equilibrium of the game, of the mixed extension of the game gamma, then for any agent I, and for any two strategies of agent I which is in this support, the expected utility that he gets from those two strategies, given that his opponent is playing according to mu star, should yield the same payoff. And for any strategy which is in the opponent and which is in the support of mu I star, and any strategy Si prime which is not in the support, the expected utility that he gets by playing Si should not be less than the expected utility he gets by playing Si prime. Okay? So that part implies this. And whenever you have a one-sided implication, the immediate question that you should ask yourself is, sorry? The what about the other direction, contrapositive? So that's that. So does these two imply that mu star is a Nash equilibrium? And actually, that turns out to be the case. We don't have time to do the proof, but that's what we have. So for any, so that's a theorem for any mu star and Cartesian product of delta Si star. Mu star is a Nash equilibrium if and only if these two conditions holds. Okay. And so this is, again, a useful tool in finding Nash solutions. Well, let's fast. We have about 3 minutes, but let's see how we use this, again, with the Battle of Sexes game. Okay? Oh, let's leave it for. Rushing is not a good idea, so let's leave it to next lecture.